All right, well, welcome back. We are on the last section for this unit. This is 4.4c, average value and second fundamental theorem of calculus. All right, so before we talk about average value in calculus, I want to just kind of go back to your elementary days. Think about how you find the average of n numbers. So if I want to find the average, there's basically two steps, right? So what are those two steps? So the first step is you typically, add all your entries, right? And let's say add all your numbers. And then your second step is divide by your total number of entries, right? So if you have 5 test scores you're trying to average, you add up all 5 test scores and then divide by 5, right? So divide by total number of entries. Okay, well, let's take a look at something that maybe we say commonly, but we really need some calculus to figure out. Let's look at what do we mean when we talk about today's average temperature. Well, let's take a look. This is July 20th, so this is probably much different from your current temperature, but let's take a look at today's temperature as well as predictions. It's 95 degrees out right now. Now, how could I find the average temperature for the past 24 hours? Well, I could take the temperature at each hour. So I would have 24 different temperatures and then divide by 24. What would be the problem with that? Well, the problem would be that there's still plenty of times that I didn't capture the temperature, right? So a better view of the average would be maybe to take the temperature every half hour, right? And this time divide by 48. Okay, even better would be to take it every 15 minutes, right? Or every minute or every second. Ideally, we want to look at the temperature every single moment, right? So I would like to take an infinite sum, which would be an integral in calculus, right? And an integral also gives me the area under the curve. So if I take the integral, that would give me this shaded area here. Okay, so let's take a look at that. If I want to find the average temperature, I know I first want to do the same thing we did in elementary, which was add all the numbers. So in this case, I would want to take an infinite sum, so an integral, and let's go from 0 to 24. Let's let t be in hours. Okay, let's call capital T the temperature. Capital T, should we do of little t time? dt. That would give me my addition part, step 1, right? Now step 2 says I need to divide by the total number of entries. Well, in this case, my independent variable is time in hours. So how many hours have surpassed? 24, right? So I'm going to take this integral and divide by 24, which would be the same as multiplying by 1 over 24 on the outside of the integral, right? And if we'll, to be certain here, why don't we make sure our units all pan out? So capital T would be in degrees Fahrenheit, right? Degrees Fahrenheit. dt we said was in hours. So right now the integral part is in degrees Fahrenheit times hours, which doesn't make a whole lot of sense, right? But when I go to step 2 and I divide my 24, 24 is in hours also, right? So I have degrees Fahrenheit times hours over hours, which leaves me with degrees Fahrenheit, which is a reasonable unit for my average temperature, right? Okay, so if I want to let's take a look at this graph again. What's happening if I want to find the average temperature? I take this area under the curve, yeah? And then I want to divide by 24. So what I want is to find a rectangle from, we can do 0 to 24, whose area is the same as this guy. So can you picture a rectangle? Maybe it would have height around here. Does that seem reasonable? That rectangle there? I would say somewhere in the 80s, yeah? About mid-80s would be my average temperature. Okay. All right, so let's take a look at the formula for average value of a function. It's exactly what we just did. So it says if f is integrable on the closed interval ab, then the average value of f on this interval is, so just like in elementary school, you are going to first sum up from a to b. Remember we did from 0 to 24 of your function. And then divide. Now, how would we have gotten 24? How did we get 24? Well, wasn't that 24 minus 0, b minus a? So multiply by 1 over b minus a. It's a little bit easier to look at. Okay, you need to memorize this. We're going to use this a lot. This is the average value of a function f on the closed interval a to b. All right, at this point, I'd like to do a few homework examples together, or homework problems together. If you want to look at an extra example, why don't you go ahead and write down example 5, page 287. All right, so if you would like to start on your homework side and open your books to page 293, we're going to do number 45 together. Now, your book asks you to find the average value, then it also asks you to find the x value or values at which this occur. I only want you to find the average value. Okay, so once you find the average value, you can stop. Okay, so number 45, the function given, I believe, is f of x is equal to x cubed. And we want to find the average value of this function on the interval 0 to 3. Okay, so 0 is your a, 3 is your b. And we're just going to follow our formula. Remember, our formula for average value is 1 over b minus a times the integral from a to b of f of x dx. Right, sum, divide. Step 1, step 2. Okay, so b minus a is 3 minus 0, so that'll be 3. Integral from 0 to 3 of x cubed dx, right? Okay, to find this integral, or to find the area under the curve here, I need what? I need an antiderivative, right? So an antiderivative for x cubed is x to the 4th over 4. And then I want to evaluate that from 0 to 3. If you would like to, you can pull out the 1/12. I sometimes think that's easier to look at. So then I only have to worry about x to the 4th. Either way is fine. All right, so I have 1 over 12. And if I put 3 in, 3 to the 4th, well, 3 squared is 9, and 9 squared is 81, right? So I have 81. If I put 0 in, 0 to any power is 0. Okay, so my answer is 81 over 12. Right? Both of those are divisible by 3. So 27 over 4 is my reduced answer. And again, I want you to stop there. Okay, you don't need to find the x's for which this is true. Okay, I would like for you to grab your graphing calculators now, and I kind of want to show you what's going on graphically. So if you will get your graphing calculators out, please. If you need more time, just pause the video. Okay, what I would like to do is first of all graph the original function x cubed and find the area under the curve from 0 to 3 there. So first graph x cubed. And then go to your window. Looks like my window's already set for this problem. So we want to go from x equals 0 to x equals 3. Now, so that we see all our y's, x cubed is an increasing function. So when x is 0, y is 0. When x is 3, y is 27. So I just went from 0 to 30. Somewhere around there is good. Okay, let's go ahead and look at this graph. So there's the graph of y equals x cubed, graphed from 0 to 3 on the x-axis. Now go ahead and shade the area under the curve for me. So let's do second calc 7. So we want to go from 0 to 3. And there's 20.25. That's that 81 over 4. That's the area under the curve that we would have gotten had I kept the denominator of 4 inside. Okay, so that's the area under the curve. That would be step 1, the integral. Okay, now what I would like to do is go ahead and graph our answer also. So our answer was 27/4, right? So go ahead and graph y equals 27 over 4. That is going to be a horizontal line, right? So let's graph that. Okay, there's our line, y equals 27 over 4. Now, if that is the average value, then the area under the curve of that rectangle should be the same as the area under the curve of the blue. Okay, so we got 20.25 for the blue. Let's see if we get that for the area under the red curve also. So second calc 7, hit your down arrow to go down to your second function. And then I want to find the area from 0 to 3 again. And that also has area of 20.25. So we did indeed find the average value there. The average value, or the average height, if you'd like to think about it that way, is 27 over 4. Okay, this guy here. Okay, why don't we try number 46 together also? Okay, so 46, we have f of x is equal to 9 over x cubed. And I want to find the average value from 1 to 3. Okay, so a is 1, b is 3. And our formula for average value is 1 over b minus a. So in this case, I'd have 1 over 3 minus 1, so 1 over 2. integral from a to b, so integral from 1 to 3, of f of x dx. And what would you recommend for f of x here, rewriting it? How about 9 times x to the negative 3? All right, again, I like to pull out all my coefficients in front, so I'm going to take out that 9 this way. Just focus on x to the negative 3. All right, so the 9/2 comes along for the ride. To find an antiderivative here, I'd want to add 1 to the power, so that would be -2, and then divide by that. Okay. And I want to evaluate this at x equals 1 and x equals 3. I would recommend rewriting before plugging in. I think it'll be easier to see. So I'm going to pull this -2 out in front. So I would have -9/4. And I'm going to rewrite that x to the -2 as what? 1/x², right? Evaluated at 1 and 3. Okay, so -9/4. If I plug 3 in, I have 1/9. If I plug 1 in, I have 1/1, which is just 1. Okay, so we have -9/4. 1/9 minus 1 is going to be -8/9, right? Okay, and now we can reduce 9 and 9, 1 and 2, and I have 2 negatives, so that's positive. So my average value is 2. Okay, and again, I want you to stop there. You don't need to find the x values for which that's true. Okay, the second part of the lesson is the second fundamental theorem of calculus. When you see problems like these, I want you to think, oh, this is the easy type of problem. Literally takes about 2 seconds. Okay, you just have to be able to recognize that that's what they're asking. So second fundamental theorem of calculus says that if f is continuous on an open interval containing x equals a, then for every x in the interval, the derivative with respect to x of the integral from a to x of f of t dt is equal to and is equal to f of x. Okay, but before we write that down, I want to go through the proof with you real quick. It's 3 steps, so no big deal. If you'll write this expression down in your notes, and then let's see why this is going to equal f of x. Okay, I want to work with brackets first, so let's keep the d dx on the outside. Okay, I'm keeping this part. And now let's focus on the brackets. Okay, it says the integral from a to x of f of t dt. Well, what's the first thing we need to do when we find a definite integral? We typically find an antiderivative, right? I'll call it f of t. And then we want to evaluate that at x and a. So I'll make a note here. Capital F prime is equal to little f. Correct? Capital F is the antiderivative of little f. Okay, so continuing on here, I'm going to keep that d dx. So now we're supposed to evaluate capital F at x and a, right? So it'd be f of x minus f of a. Okay, we're almost there. All right, now I want to take the derivative of this expression. Remember, difference rule tells me I can take the derivative of this minus the derivative of this. Okay, well, the derivative of capital F is equal to what? Just little f, right? So my first piece is just little f of x. Now notice what this guy is. This is some function evaluated at a constant. So my answer here, like if a is 2, some constant, then this has to be some, maybe a different constant, right? Regardless, this piece is a constant. And what's the derivative of a constant? Well, 0. So that's how we get f of x. Okay. So whenever you see something weird like this, all you have to do is take that x, put it in for the t, then your answer will be f of x, whatever your function is. Okay. We'll do a couple examples. These are, again, real fast. This is number 74 on page 295. All right, it says g of x is the integral from 0 to x of f of t dt. Okay, well, if I take the derivative of both sides, let's do d dx. Ooh. Well, the derivative of the left side is just g prime, right? The derivative of an integral, that's the second fundamental theorem of calculus. So that's where I just replace this kind of dummy variable t with this variable here, x. Remember, derivative and integrals are really going to kind of have this cancellation effect on each other. So the right side simply becomes f of x. And that's literally it. Okay. Let's do a couple others. Let's say g of x is equal to the integral from x to 5 of f of t dt. Okay, if I want to find g prime, if I differentiate this side, I would get g prime, right? Well, hold on one sec. What do you notice about the right-hand side? Notice that for the second fundamental theorem of calculus, my constant was on the bottom and my variable was on top, wasn't it? Okay, so why don't we go ahead and rewrite g of x? If I flip the limits of integration, I just need to put a negative there, right? So negative integral from 5 to x of f of t dt. And now our integral looks more like how we need it for the second fundamental theorem of calculus. And this negative will just come along for the ride. Okay, so if I differentiate both sides, the left side becomes g prime. The right side, that negative comes along for the ride. Derivative and integral will cancel each other out, and my new independent variable will be an x. Done and done. Okay. What if I had something like this? G of x is equal to the integral from 0 to x squared of f of t dt. What's different about this one? Hopefully you notice that you have an actual function here other than just the identity function x. So when I take the derivative of a function inside another function, what rule do we need? We need chain rule, right? So we're going to do this the same way. You just need to remember that at the end, we're going to need to multiply by the derivative of the baby. Okay, so the derivative of x squared is what? 2x, right? So at the end, we're going to need to multiply by 2x. All right, so differentiate the left side, g prime. When I differentiate the right side, the derivative and integral are going to cancel each other out. This guy gets put in there, so I get f of x squared, right? Again, don't forget to multiply by the derivative of the baby. So just multiply by 2x at the end there, and that's it. Okay. So one last example. Let's say g of x is equal to the integral from -2 to x cubed of sine of t squared dt. All right, so first of all, this is correct order, right? Constant on the bottom, variable on top. But hopefully you notice that you have something that's going to require chain rule here. So differentiate the left side, you get g prime of x. Differentiate the right side, that derivative and integral are going to have that cancellation effect on each other. So we're going to replace t with x cubed. So take the stuff inside, sine. So now I need x cubed squared. So x cubed squared is x to the 6th. Then don't forget to multiply by the derivative of the baby at the end. And that's it. Okay. All right, I thought we would take a look at AP Set 5C if you'd like. So if you want to go ahead and grab your AP set, I want to take a look at part D. Okay, so hopefully you have it in front of you, but it says on a certain workday, the rate in tons per hour at which unprocessed gravel arrives at a gravel processing plant is modeled by G of T, where T is measured in hours and it's between 0 and 8. At the beginning of the workday, T equals 0, the plant has 500 tons of unprocessed gravel. During the hours of operation, the plant processes gravel at a constant rate of 100 tons per hour. And I would like to look at part D. Of course, you can look these up on AP Central, but I kind of want to walk you through part D. Keep in mind this is calculator active. Be sure you are in radians. Okay. Part D says, what is the maximum amount of unprocessed gravel at the plant during the hours of operation on this workday? Justify your answer. Okay, so the first thing we would like to do is write a expression involving an integral that just gives us the amount of unprocessed gravel. Okay, and then how would we find a maximum of some function? Well, to find a maximum, we find the derivative, right? Set it equal to 0. Now we want an absolute max. So in this case, I also want to consider the endpoints, right? So I want to do a candidate test and consider 0 and 8, right? So first thing we're going to do, again, just to walk you through it, is find an equation for the amount of gravel at any time. Then we're going to take the derivative and set it equal to 0. And then we're going to create a table and figure out which time gives us our maximum amount of unprocessed gravel. All right, so let's try it here. Okay, so A of T, the amount, is actually going to be a final equal start plus change guy because we started with how much gravel? We started with 500, right? Then we change at a rate of, well, gravel comes in at a rate of G of T, I believe. Yes. So I'm going to put G of X here. And it goes out, it's processed at a rate of 100. Okay. So this will be from the starting point to time t. Okay, so this gives me the amount at the plant at any time. So I started with 500, and then my change is going to be my in minus out. So it's coming in at a rate of g of x, going out at a rate of 100. Okay, so if I want to maximize this function, couple steps, I take the derivative, set it equal to 0, right? And then I create a table. So a prime of t, well, the derivative of 500 is 0. And then the derivative of an integral, here's where that second fundamental theorem of calculus comes in, is simply g of t minus 100, just replacing this x with this variable here. Okay, so I would like to know when the derivative is equal to 0. So in order to do this, remember this is graphing calculator active. So I would probably do this when g of t is equal to 100. Okay, and then go ahead and graph g of t and like y1, 100 and y2. Be sure you're setting your window from 0 to 8 on your x's and at least up to 100 on your y's. Probably more like 120 or so. And then see where those intersect. Okay, those only intersect at one point, and I want you to go find that. I'm getting about 4.923. Now, it is really important, guys, that you do not round until the end, right? Because that could mess up your end decimal by a teeny bit, and then you could be marked off. Okay, so that is where the derivative is 0. There's only one place, so that makes our table not too bad to construct. So I'm going to look at my times, and I'm also going to look at my amounts because I want to know when my amount is greatest. So I want to consider this 4.923480. I'm just going to call it A so I don't have to, oh, not A, we already used that letter. I'm just going to call that B. So I need to use my endpoint 0 and 8 and that 4.923480, or what I'm calling B. Okay. All right, so to find A of 0, you're going to come back to your original function here. Okay, so, and you can type this in your calculator, do 500 plus the integral from 0 to 0 of g of x minus 100 dx. All right, but integral from 0 to 0 will be 0, right? So I know this guy is just going to be 500, which makes sense because that was my starting amount. Okay, for your amount at time B, at this 4.923480, type in 500 plus the integral from 0 to 4.923480 of g of x minus 100 dx. Okay, and you should get about 635. Okay, now we just need to see what it is at time t equals 8. So again, go to your calculator, type in 500 plus the integral from 0 to 8 of g of x minus 100 dx, and see if you get less than or greater than the 635. And you're simply going to choose your largest number. So I know it's either this guy or this guy, right? 500 is too small. And that will be your maximum amount of unprocessed gravel at the plant during the workday. All right, so go ahead and finish those. Definitely check AP Central so that you are getting the correct notation and wording there. And that is that for this unit, guys. So good luck with the studying, and I will catch you all next time.